wanted to thank Richard very much for inviting me here and for his long-time support of this project. He was enthusiastic right from the beginning about this idea of benchmarking causal discovery algorithms that we got into since 2007, I think. And there's a lot of people that are involved into organizing challenges, so at the risk of not having enough time to speak to the end about what I want to talk about, I really want to first thank all the people who have been involved. First of all, the co-founders of the Causality workbench that I'm going to talk about today, which include Konstantin Aliferis, Andrei Elisseff, Greg Cooper, Alexander Statnikov is here today, Jean-Philippe Perret, and Peter Spirus, who is here also. And since then we've grown, and we now have a nonprofit called Chalearn, and we have several people serving as directors and advisors, including Richard Charnes and Ionis Samardinos and Frederic Eberhardt, of whom are here in this room, and Florian Popescu and Alexander Snadnikov. And I'd like to thank also the Pascal II Network of Excellence, who's been funding us, and also the NSF. And this work wouldn't make any sense, if there hadn't been so many participants to our competitions. We've had, hundreds of people who entered our competitions, to whom we are extremely grateful, because they donate their time to solve these hard problems, and sometimes in ways that are very unexpected and very different from what the traditional literature is doing. We've had also prizes that have been donated to encourage participation, and I'd like to thank a lot, all the diverse sponsors, sometimes who are very small companies. And there are a lot of people who are involved into the organization, and we keep, involving more people, and we hope, that some of you will be joining after you get excited about the result that we've obtained. And we like, disseminating our results, so we need editors, and we have people who've been donating their time to edit proceedings and also to publish the books. The books that we have free PDF, and they are published on demand, so they're very inexpensive. They're like $30 a book, so don't hesitate to order them on Amazon. The whole effort is impossible if people don't donate their data. And this has been very, rewarding to see that some people don't just sit on their data to produce their own papers, but they like to share their data and see and put themselves at risk, to have their own results dwarfed by the results that other people get on the data that they release. And finally, I'd like to thank the public, which includes you, people who attend talks of reporting results of competition, or talks from people who participated in competitions, who are sometimes very knowledgeable about how to present their work, because those include engineers who've never given any technical talk. And we're going to have soon a workshop at the Neural Networks Information Processing System Conference, the NIPS conference in Tahoe, where we're going to report the results of our last challenge. And if you have a chance, I would like very much to encourage you to come. This is going to be a very exciting workshop. So, this advertisement. So now what makes our effort different from other efforts of benchmarking that happens in machine learning and data mining? We haven't been specifically focusing only on causality. We've been organizing many different kinds of challenges, but causality is one of our pet projects, because it's so challenging and so interesting to benchmark causality algorithms. And we had to put together a completely new type of platform to do that we call the Causality workbench, and that includes a virtual laboratory. As many of you here know, to really validate causal relationships, you need to perform experiments. But in the context of organizing a benchmark or a challenge, performing actual experiments is almost impossible. You couldn't have 100 plus participants of a challenge perform real experiments on a real system. So we had to come up with the idea of creating a virtual laboratory where people could be experimenting on realistic simulators of real systems. And so on the right side, I represent a simulator of a real system. And on the left side, I represent the interface that the participants will experience. The participants, they place queries, they ask for data to the simulated system, and then they get answers from those queries. And then they have to derive models and make predictions. So this differentiates our approach from other data mining challenge platforms, because in data mining challenge platforms, people get frozen data, so pre-recorded data. And they get, to make predictions on one of the variables which is, hidden, one of the columns of the table, for example, which is hidden. And for example, typically they need to make predictions of diagnosis of a disease given some clinical variables. But if you want to benchmark experimental design or to benchmark algorithms where you don't just get frozen data, but you get to query the data generating model, you need to have a completely different approach. Now the data are not frozen anymore. You're not dealing with a data table. You're dealing with a model that generates data on the fly, on demand. So this is what we've been doing. And for example, a typical usage would be that you initially download some observational data that simulates, a survey study. And then you try to tentatively to predict a causal structure. Then you design some experiment, and then you submit a query to the artificial system to ask for more data. And that query represents some experiment that you have designed to ask for more data from the system. Then you retrieve more data, the system gives it back to you. You pay some virtual cash because it costs to perform some experiment. And then you iterate that. And the challenge that is put together by the organizer is such that you have only a certain budget of virtual cash that you can spend. And at the end of the challenge, you need to deliver your prediction results, your final prediction results. So we've been working in that spirit, and one of the first challenges we organized to use our platform is a challenge in active learning. So that's closer to classical machine learning than causal discovery. In that case, the experimental setup is just that you get a lot of unlabeled data, and what you can query for is the labels of the data. So you have, for example, a classification problem in which you want to predict, as I said, a given disease. And so you would get a lot of clinical variables from a lot of patients, but you would not get the outcome unless you ask for it. And you can ask for it only for a certain amount of virtual cash. But actually, in that case, the way we set it up is that every time somebody queried for a label, what he had to pay is just give his prediction onto all the labels that are not provided yet. And in this way, we could build a learning curve. So every time you ask, for a certain quantity of labeled data, you had to give your predictions on all the data that was not labeled yet. And here we see the plot of performance in terms of area under the ROC curve, which is a metric that we use for measuring classification accuracy. So 0.5 is random predictions, and 1 is perfect prediction. So if you have only one labeled example, you're actually doing worse than random predictions in that case for that particular participant. And as you get more and more labels, you move towards better and better predictions. So far we've organized a number of challenges, and some of them use the virtual lab, some of them are in a more conventional setup of frozen data. And I want to take just 2 examples of challenges to see the kind of results that we are getting. The first one is more of a negative result, even though we only admit it once. We have now positive results. When we did the challenge, we didn't really say it was a negative result. So, anyways, the first challenge we organized back in 2008, we called it Causation and Prediction. So one thing which is extremely difficult, and we've talked a lot about it today, is figure out a way of quantitatively assess how good the models are doing in terms of predicting causal structure. And in many settings, you don't even know for sure what it means that A causes B. And in many settings, you don't even have a ground truth of the causal relationships. So we tried to devise a challenge in which we didn't really need to get into that level of details. We would indirectly infer whether the model was good or not through a given task of prediction. And we made it such that if you discovered the causes of a given target variable, then you would be better off than if you would do classical feature selection or classical regression on all the variables. So we used a number of data sets, and I will explain briefly, how we created artificial data and semi-artificial data. So the goal is to predict one target variable. So here I'm using a toy example. So the data were not generated from this, very small example, but to explain you how we set up the challenge, it's easier to use a small graphical model. So imagine that what you would want to predict is lung cancer, and that all the other nodes on the graph are other variables that might be predictive of lung cancer. Some of them might be causes, some of them might be effects, some of them might be related in a more remote way, and you may have variables that are not related at all to lung cancer. Now the idea is that you want to make predictions of lung cancer given other variables. So people are going to get a data table of instances, representing patients in that case, and values for all these variables. And the lung cancer outcome is going to be present only in training data, and in test data, you'll have to predict it. So if the data are strictly observational, then you are in a classical data mining or machine learning problem. And potentially all the variables could be used to make predictions, except that if you want to have a parsimonious model, maybe it would be sufficient to use the Markov blanket, which is the set of variables that shield the target variable lung cancer from the other variables, and they are sufficient to make predictions under the assumption that you have enough data. So we would be expecting that if people do some feature selection, they would put more emphasis on the Markov blanket variable. Now, what would happen if now we would start manipulating the distribution and do some experiments on this system? Well, it would have the effect, here I'm representing in circle red the variables that are being manipulated. It would have the effect of isolating these variables from their causes. And what we expect that if we manipulate a lot of these variables, in the end, only the variables that are the direct causes of lung cancer might become relevant to predicting lung cancer. Or at least, there will be much fewer variables that will become relevant. And so now, knowing the causal structure of the system will help you to make predictions, because you're getting more and more variables that are irrelevant and that are just, noise variable. The more variables are being manipulated. So indirectly, we've been putting pressure on the participants to have a causal model behind their predictions, without asking them precisely what is the structure of that model. Now, I was saying that we were not using only artificial data that we could generate from a model such as the one I was showing, but we would also use real data. So for real data, we couldn't actually perform experiments because we didn't have the luxury of doing actual experiments. So we resorted to having a semi-artificial system. So assume now that the system I'm showing here is a real system, but it's a system of which we don't know the structure at all. It just generated examples that are pre-recorded. What we would do is to add additional variables that we call probes that are artificial variables. And so we wrap the real system, which is now all the oval nodes, into a bigger system that contains artificial variables. And now for those artificial variables, we have the possibility of manipulating them. And so they serve as control. So if now the participants go and select those probes in manipulated data, we know by constructions that they are completely irrelevant to predicting variables. And here we know by construction that which variables are or not part of the Markov blanket. And so this is the data we give to people. Now the results were very surprising to us. The results were that in fact, people who used causal discovery to perform their prediction didn't do much better than people who knew nothing about causal discovery and just applied plain machine learning methods, even in the case when we had manipulated data distribution. We manipulated data in different ways, so I don't want to enter into details, but we had the distribution 0 is the natural distribution without manipulation. 1 is kind of a mild, way of manipulating data, and 2 is really adversarial. We really, made it that we wanted the participant to fail if they didn't use causal discovery. So one participant here used causal discovery methods, and the color coding is such that if he selected direct causes, it's dark blue. If he selected other causes that are including indirect causes, it's slightly lighter blue. And these are afterwards. And cyan is direct effects, green is other effects, orange is causes, red is other relatives, and brown is unrelated. So just visually, you can see that the guy who used causal method, he had a lot more dark blue in the selection of features that he had than the guy who didn't use causal discovery. But if you look at the performance that they obtained, which are here, how well they did in terms of area under the ROC curve and how well they ranked on the 4 tags that we put out. So for each of the data sets, we had natural distribution and 2 manipulated. And we had 4 different data sets, Reged, Sido, Sina, and Marty. So the first guy, he ranked, in the challenges 3rd, 5th, 4th, and 2nd using causal discovery method, and the other one ranked 4th, 6th, 2nd, and 4th, out of several hundred participants. So this was kind of a surprising and negative result in a way, and we wanted to understand that, so we did a very simple analysis that I'm briefly explaining here. So that goes back actually to some of the talks this morning regarding or not whether we want to consider the connections in our model as structural or not, and whether we really want to cut a variable from its parent or its descendants when we make predictions. Well, as it turns out, when we make predictions, we want to be very conservative. We don't want to make mistakes. That is, it's much more costly to your predictive power to exclude a variable that is potentially predictive than it is to include a variable that is not predictive. Right? So you can have a lot of garbage in your predictor variables and be totally insensitive to it. And that's, in fact, something that we have noticed over and over again throughout the years, even in the first feature selection challenge that we organized that had nothing to do with causality. We added a lot of these probe variables, which were complete garbage variables, to see how people were doing at excluding garbage that we knew for sure were completely unrelated to the target variable. And much to our surprise, some people just completely ignored that. They did not perform any feature selection at all, and they performed very well at predicting the target variable. So why is this? Well, it's not so surprising after all, because if you have a lot of data, the weights that correspond to completely unrelated variable, they will fade away, right? They will have zero expected value, and the only way in which they are contributing noise to your predictions is through the standard deviation of the weight, not through the expected value. And the standard deviation, it only scales with 1 over the square root of the number of examples. So it goes down, as you have more and more examples. And the contribution of the noise variables to the total input is scales like the square root of the number of bad noise variables over the square root of the number of examples. So that's in the case of the unmanipulated data. So what happens if you have now manipulated data? So what we ask the participants to do is to train on the natural distribution. The only thing that they had was data from the unmanipulated distribution. And then we asked them to make predictions on the manipulated distribution. So there was a nasty problem. Well, even in this nasty case, the worst that can happen to them is that they take into account the bad variables, right? So they give them a weight of 1, a weight that is as important as the real good variables. But in the end, if your manipulation method is not nasty, and if you just assign random values to your variables that are irrelevant, they were going to cancel each other out if you have many of them. So on average, you will again have an expected value of 0, and it's only going to contribute with the square root of the number of variables. It's only in the case where you have an adversarial manipulation. You don't assign random values to your useless variables, but you assign them the exact opposite value than the value that it would have if it had been connected normally in the original network. Only if you do these adversarial manipulations do you contribute really a nasty, a hefty penalty. All right, so. After this, we decided that we would open up the competition design to the public. We said, okay, we're not smart enough to design a good competition. Let's have everybody try to submit good problems and good ways of benchmarking causal discovery algorithms. And so we had many people contribute very interesting problems. I don't have time to go over all of them. I just want to focus on the last one, which is the cause-effect pairs problem that was proposed by Dominic Jansing and his collaborators, because that was the inspiration for the next challenge we organized this year. So we've talked a lot today about inferring causal graphs with multiple variables. And it seems like it's the holy grail of causal discovery. When you have a lot of variables, that's when things become complicated and interesting. And if you omit the really crucial variables, you might get completely wrong results. We've heard that over and over again. And everybody has heard, about Simpson's paradox and about, the bad effect of confounders and all of these horror stories of causality. Now, the other thing that we've heard a lot about today is that it's very difficult to infer the right causal structure in a graph, and in particular if you don't have enough samples. If you have many variables and very few data samples, then you may get complete garbage. Then you don't have stability of in your predicted graph and so on. And if you think about it, it's not so surprising, right? Because if you do conditional independence tests, the more conditions you have to check, the more data you should have. So presumably, you need exponentially more data in the number of variables you're conditioning on. So that's really horrible. It's a horrible case of the curse of dimensionality. So this has happened to us before we got interested in causality. Before we were interested in causality, we were doing feature selection. And so it was not as nasty a problem. We only wanted to make predictions. We didn't necessarily want to predict the consequence of experiments. That is, instead of being in the case of diagnosis, to speak with medical problems, we were not in the case of drug discovery in which you want to know whether you're going to affect or not your outcome by making some changes. But still, we had this problem because, for example, we were interested in genomic data, and you wanted from gene expression microarray, you had only 100 examples to be making prediction of cancer or non-cancer. And all the people who were doing multivariate analysis and tried to do feature selection with multivariate analysis on 100 examples, they were overfitting very badly. And so they turned to univariate methods. So they said, okay, forget about all these fancy methods to look at data with multivariate models. Let's just use Pearson correlation coefficient. Right. Well, as it turns out in practice, this works often better, especially if you have very, very few examples. So this is a lot of background for what we wanted to do here. We said, okay, forget about all these other variables. Let's consider only 2 variables. Now you're going to tell me, oh no, we can't do a causal discovery with only 2 variables. Who is doing something like that? Well, some people at the Max Planck Institute in Germany really got very interested in that, and they developed a lot of methods and they developed a lot of theory about identifiability of causal relationships when you have only 2 variables. And this has potentially many applications because sometimes you only have 2 variables, and you know that there are more variables than 2 in the world, but you don't know how they are affecting these 2 variables you're interested in. And sometimes you have very few samples, so even though you have all these variables, you are in that case where you're better off considering only 2, even though you know the other ones. So we set up a challenge in which we told people, we're going to give you only 2 variables. Well, are you telling me if there are only 2 variables, there is 50% of chance kind of being correct, that A causes B or B causes A, so you might as well play the lottery, and half of the participants are going to win and the other half are going to lose. It's not very much fun. So in order to counteract that, we provided people with a lot of pairs. So they had to solve many, many, many times the same problem: does A cause B or B cause A? And in fact, we made it a little nastier than that. We generated data in which we had A is a function of B and some noise, or B is a function of A and some noise, or A and B come from a common cause, or A and B are completely unrelated. And we asked people to create what we call a causation coefficient, which is a number that is high and positive if A causes B, small and negative if B causes A, and is 0 if the variables are independent or they are caused from a common cause. So the typical method that people can use to resolve such a problem is to compare 2 models. Is B a function of A and some noise, or A a function of B and some noise? And I'm stressing here that we are not assuming that there is additive noise. So it's any combination of A and some other factors. And the other factors don't need to be Gaussian. So we're not making any assumption about this F here. F can be anything. And noise can be anything. All right. Now, here's the intuition. It's kind of a lame intuition because we've heard about so many sophisticated algorithms here. But intuitively, if you have a non-invertible function, for example, second-degree polynomial, then when you try to do the fit, if there is no noise, then you can get an excellent fit if you fit in the right direction. But if you fit the backward model, you get a very poor fit. And if you have, a lot of points, maybe you're going to get, a jaggy line for the fit, or you're going to, if you regularize, then you're going to get this green line that I'm showing as the estimator. So the residual is very bad for the second model, and it's very good for the first model. And so you say, okay, great. Based on the residual, I'm going to say that A causes B. Now you can apply that to some real data, and it still works pretty well. So here, actually, A is altitude in German cities, and B is temperature in German cities, and it's on a log scale. So you see that if you do B as a function of A, you get a pretty good fit, and if you do A as a function of E, this is done with some radial basis function, you get a much worse fit. So it's not the only way, you can solve these problems. People have been proposing a lot of different ways, additive noise models, Lingam, Gaussian processes, information geometry. So I refer you to the webpage of the Max Planck Institute for many references of many interesting algorithms. And some of the game these people have been playing is to define which cases are identifiable or not, depending on various assumptions. And this has very much the flavor of Frederick's previous talk, so he really laid the basis for that. So then I asked, the Max Planck people, well, it looks like you really have solved the problem now because you've covered all the cases. So do you have a piece of code that I can use, and given no prior assumption about the data, I can tell whether A causes B or B causes A? And they said, well, not really. It's all different. Every model is different. It depends on the case and da-da-da. So here, here comes actually Alexander Statnikov, who's here, and Alexander said, I'm just going to try all these algorithms on some tasks and compare and see how they work. And he did that in some very interesting paper in which he used transcription factors in genomic networks for which he knew which genes were triggered by which genes were expressed when these transcription factors are being expressed as the ground truths. And so he made these comparisons and also voted between different models and got some very promising results. So we thought, okay, let's set up a challenge in which we give lots and lots of pairs and see whether people can do even better than just these baseline models or voting between these baseline models. So we have a very large data set, and it's composed of about 18% of real data that's made of pairs for which we have a good intuition of what the ground truth is. So it might be wrong in some cases, but in a lot of cases when you take all these data mining databases that we've accumulated over the years, there are pairs for which we can say pretty confidently that there is a certain orientation of the causal relationship. So we use those as real data. And we use artificial data generated by lots and lots of different functions and noise models. So first, we actually made a mistake in normalization. So this is tricky to generate artificial data, because if you have some artifact, people will catch on it very easily. So that's, in fact, speaks in favor of organizing challenges. If you have 200 participants scrutinizing your data, and you have a bad data generating model, the likelihood that one of them will find out is very high. And we were lucky in that case, because the person who found out there was a bad artifact in our data, instead of taking advantage of it, sent us email and said, look, I think there's a problem in your data. If we do this and that, then we can get beautiful results, but it's not really meaningful. And we said, oh, gee, yeah, that's right. Our normalization is stupid. So I regenerated the data, and a lot of people complained because they already had great results with the bad data. I had a whole lot difficulty explaining them that it was completely worthless to have good results on bad data. And well, they said, oh, okay, but from now on you have to freeze the data. So we had to release encrypted test data to prove them that we wouldn't be fiddling with the model anymore. And they were satisfied, and they kept working on it. And we also produced, more and more data for them to train on. So the characteristic of this challenge is that people got a lot of training data, a lot of pairs that they could build their model with. And it's very different from what other people did before, because before people used principled models that were not trained. They made assumptions about how data are generated to produce B from A. But they never took plenty of data that was generated by a huge amount of different ways and tried to figure out whether they could make something out of it. All right, well, the results were stunning, and you'll know more if you come to the next workshop, in Tahoe in December. It's again my advertisement. So the results were, much beyond our expectations. So all the baseline methods that were, derived from principled theoretical arguments, and that Frederick described in his previous talk. All of those methods, they kind of had performance between 0.5 and 0.6 in area under the rock curve, which is the metric that we used here. So 0.5 is random, right? And 1 is the best value. And if you, vote and so on, you get maybe in the 0.6 range. But the participants of the challenge, they got in the range of, 0.8 AUC, right? The top one is 0.82. So this is very remarkable. And we're still, with Alexander trying to validate these results. And we have the code of the top-ranking participants. So we are now, torturing their code by submitting it to other data generated in different ways, or any data that we can think of. And we're even going to organize a follow-up challenge in which we're going to put, the algorithms on a platform where people can submit new data sets or new algorithms, so in a more, interactive way, because we really want to validate these results, which I think are very powerful. And I'm sure you're curious to know, but how did they do that, right? How is it even possible that you get such a big leap in performance by basically inverting a problem? These people, they just use the brute force, right? Brute force data mining. So the people participating in this challenge have no knowledge about causal discovery, and most of them. I mean, some of them do, some of them read the papers and try to engineer features. But okay, the top-ranking participant, he had no knowledge of causal discovery whatsoever. Right? The only knowledge he had was what we explained on the website, what the task was. And so what he did is that he said, well, okay, we want to know whether A is a function of B plus noise, B and some noise, or A is a function of B and some noise, or B a function of A and some noise. Well, we know how to do that, in data mining. We have these big libraries of predictors. And so let's just take one of these big library of predictors that has many models, many cost functions, many regularizers, many ways of filling with the hyperparameters. And let's also take all the possible statistical tests that we know about independence between variables. And using those, let's generate a lot of features. Features such that, what is the residual of the model, what is the correlation between the residual and the input, what is the difference in residual between modeling in one direction and modeling in the other direction. And in this way, he generated 9,000 features that then he put into a model that, in that case, is a boosting model, but other people used random forest. So those were the two most popular ways of then integrating all the lower level, features. And then he made predictions. So one of the ways was simply to just do a regression on the outputs that were 1 for A causes B, 0 for it's not a causal relationship, and -1 for B causes A. So ultra simple in principle, but very powerful because it involved a lot of low-level features that characterize the joint distribution of the variables. So that was for the top-ranking participants. The other participants that rank just almost as well, because given the error bars, their performances are not statistically different. The other ones used fewer features, and some of them included in their features the results of the algorithms that were proposed in the literature. So at any rate, I think that we have now a very powerful tool to orient the direction of causality when we have only a pair of variables, and that we can include as part of, as kind of a building block for other algorithms, or in some cases maybe used by itself if we only have two variables. So what's next? So for people who have been at some of Pearl's lectures, he likes, saying that causal discovery is an inverse problem. But usually in his pictures, the nice picture is the real world, and the ugly picture is the projected world. So here we have the projected world, which is the nice world, and the real world is the nasty world. So we want to organize more challenges. And in our pipeline, we have a bunch of challenges on experimental design. And we're working on one with gene networks, one with real neural networks. And we're thinking of a lot of different types of realistic simulators of causal systems. And we're hoping, that you're going to help us identify good simulators of real systems. I'd love to have one in econometrics, for example. Really, kind of a substantial big simulator of making a very, very complex dynamics, that is not a simple SAM or a simple, Bayesian network, but something with lots of feedback loops and bizarre things in the nodes. And then we also want to continue exploring more this cause-effect pairs problem. CodaLab is a platform that Microsoft is putting together. I was just alluding to it. What we want to do is to put a lot of data sets and a lot of algorithms solving this problem and put them in relation and see what works and what doesn't work. And then we would like to do a causality in time series, because this time the cause-effect pairs challenge, maybe I didn't even say it, came only from variables that did not involve the time component. So there is the A, if B is a function of A is IID samples. Okay, so with that, I would like to thank you, for your attention, and hope to involve you into either the participation or the organization of challenges. Bring your own data, design your own challenges. I think this is very powerful, and it's only the beginning, and we're very excited that the community of machine learning is ready to solve these hard problems, and I hope that you're going to fuel more such hard problems to them. Thank you.
Just a brief question. So the score was, you have to specify with the causal coefficient that you mentioned. That specifies is that a structural coefficient, or is that a quantitative coefficient?
Yes.
Because I guess what I'm asking is that I may be very good at estimating the or fixing the orientation, but terrible at getting the quantitative features.
Yes, so the setting we have may be puzzling to the causal discovery community. We're thinking more in terms of, we're not thinking necessarily that there is a true underlying causal relationship, right? But we're assuming that it's meaningful to think in a way that A might be generating by as a function of B and noise, or B might be generating as a function of A and noise, and we want to know what is the more probable model, because that might be useful, right, if we want to do some intervention. So what we ask people to do is essentially to solve this classification problem, Can you answer the question whether this joint distribution that you see belong to the A generated B class or to the B generated A class, or neither? So as a classification problem, we ask people to give a discriminant value that discriminates between these two categories. And this discriminant value is used to rank the solutions and calculate the area under the ROC curve. Like we do, in classification, usually. We have a discriminant value. And so for those people who are not familiar with the area under the ROC curve, you can calculate in a classification problem the error rate of the positive class that you might call sensitivity and the error rate of the negative class that you might call specificity. And you have always a trade-off between sensitivity and specificity depending on how you set the threshold on a discriminant value, which is large and positive for elements of the positive class and small and negative for elements of the negative class. So if you provide a discriminant value that is this, kind of a continuous number that gives you confidence or not that you belong to one class or the other, if you want to ignore the fact that you need to set a hard threshold to decide whether it's on one side or on the other side of the decision boundary, you might be using this area on the ROC curve, which is the area under the curve that plots sensitivity as a function of specificity when you vary that threshold. I didn't want to enter into that level of detail. Essentially, you have that score, and if it's 0.5, it means that you have random classification. If it's 1, it's perfect classification, and in between, you have a degree of how accurately you're predicting the correct class, which in that case is A causes B or B causes A.
Let me urge you to ask Isabelle any questions later or tomorrow, because it's so late and her bus is waiting for speakers. Let's close and say thank you